Welcome, math enthusiasts! In the next 10 minutes, we are going to learn about algebraic and transcendental numbers. The information you find here may be useful in clearing up any misunderstandings that you may have, all of which can be found in the PowerPoint slides that is attached below.
Algebraic and transcendental numbers. Alright, so according to the online lexical Oxford Dictionary, algebraic is defined as a mathematical expression or equation that includes a finite number of symbols combined using only addition, subtraction, multiplication, division, and exponentiation with constant rational exponents. On the other hand, transcendental means relating to a spiritual realm or something that does not obey the laws of this realm. It can also mean not a root of an algebraic equation with rational coefficients. Well, if you got lost in all those words, no worries, let's try again. Starting with algebraic numbers. From what we can see, this refers to numbers that are related to algebra. Algebra is the branch of math where we have symbols and formulas consisting of x's and y's together with a bunch of plus, minus, and multiply symbols, right? In actual fact, algebraic numbers refer to exactly that. Algebraic numbers are those that we can create with algebra. So, if we can make it using algebra, then that means there's a function out there that can unmake it. What I mean is, there exists a function fx such that if x is our algebraic number, it's possible for fx equals to 0 to exist, to make it to become 0. We call these functions polynomial functions. For example, we have 3. Easy, right? Just minus 3. Same goes for negative 5. Just a plus 5. A quarter, we can have fx equals to 4x minus 1. Now, a radical function. A radical function is, for example, square root 3. It looks like it has infinite number of decimals, but is it algebraic? Sadly, it still is. We can have the equation of x squared minus 7. Now, 2i. For your information, I is the imaginary number of square root of minus 1. Surely, something imaginary must not be limited by strict algebra rules, right? But we're still in algebraic. We can see that the natural numbers up here are a subset of integers, which is a subset of rational numbers, which in turn is a subset of real numbers, including radical. Real numbers and complex numbers are both the subset of the huge family of algebraic numbers. So what numbers are transcendental? Well, before we get to that, let's first understand what transcend means. Literally, it means to go beyond limits or to surpass something significant. In our transcendental numbers, it means that our numbers have transcended the tools of algebra and we can't create those numbers from silly things like addition and multiplication. These numbers are beyond our means of creating numbers and can possibly go up to an infinite number of decimals. In a nutshell, if we let any transcendental numbers to be x, it's not possible for a function fx to exist such that fx equals to 0, which means that we can't deconstruct it to become 0 with algebra tools. Hard to imagine, right? Actually, we even started learning about transcendental numbers since primary school. Remember pi? The one from pi r squared. That's right, we use pi, a superstar in transcendental numbers, for calculating circles. According to the website The Verge, a Japanese Google employee has set the record of calculating more than 31 trillion digits of pi. There are quite a few ways to calculate decimal places of pi, but are rather sophisticated using long formulas. How about we try something rudimentary?
As we all know, to find the circumference of a circle, we need to multiply the diameter of the circle with pi. Why is this true? Well, as we know that circumference and diameter are both directly proportional, we can see that there is a certain ratio at which both numbers increase or decrease together. Thus, to find this ratio, we just have to divide the circumference by its diameter. Now, time for a little exercise, shall we? You'll need a compass, a mathematical one, mind you, not the golden one that predicts the future, okay? Alright, so a compass, a string of 30 cm, a ruler, a piece of paper, and a pencil. If you don't have a compass, a bottle with a round surface, with a round base would be good. So the next step that we want to do is we're going to draw a circle with our compass set at, say, 3 cm apart. The circle's diameter would be 6 cm, as I've drawn. Any number will suffice, but it has to be neither too small nor too large, because our next step on the list is to place the string with hook on top of the circle we drew. Place one end. Okay, before that, let's draw a line first to indicate where we started. So we're going to put it here like this, and we're just going to follow the round end. Then we're going to keep it up until we reach the starting line. Okay, then we have the point of where we stop, and this is the circumference of our string. Then we put it here and draw a line here to indicate we started here, and we're going to draw it out and indicate the end. So if we measure it, we can see here is 15 cm, and we have another 4 cm. We have 3.9.
So what we need to do now is to calculate circumference divided by diameter. So 18.9 cm divided by 6 cm, we have 3.15, which is quite close to our pi, right? Just from this most basic method of calculating pi, we only have a small error of around 0.27%. Not bad. Another interesting fact, if you ever can't find the pi symbol on a calculator, a good substitution would be the cube root of 31, which has a value of 3.1413 and so on. Whereas our pi value is 3.1415 ... Now onto the next member of the transcendental family that's commonly used, the exponential constant. Also called the Euler's number, E is a very interesting and important constant that is widely used in many areas of expertise. To be precise, anything in nature that increases at a speed that keeps increasing is a function of E. For example, the exponentially increasing population of the human race. Even our universe expands at an exponential rate of E. Now, time for a trip down memory lane. Remember that day when your dad or mom or both brought you for the first time to the bank? You were told that the money in your bank becomes more every year, right? Maybe 2% or 3% per annum. Then, did you ever wonder why you got interest every month? Well, in actual fact, banks count interest rates daily. Look at this. Does it look familiar? This is indeed the compound interest formula that you used before or are going to use in secondary school. What we want to do now is to see what will happen if for 1 year we deposit $1 of principal in a bank that generously has 100% interest rate. Then we'll have an equation of n, where n is the number of times it is compounded. In layman terms, it means how frequently that the interest rate is counted. So, if we limit n to infinity, or letting n to be a very big number, what would you get? In actual fact, you will get 2.71828 blah 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 and so on. And yes, this is the value of E. So what is E in context of our example? It is in fact the growth rate of $1 in a 100% interest rate bank for a year. An exponential graph as shown in this graph. A mathematician by the name of Joe von Schneider had proved a theorem that states that two algebraic numbers, a and b, can form a transcendental numbers. If a is neither a nor 1, is 0 nor 1, and b is an irrational number, we can place them as such that a to the power of b is a transcendental number where its decimals can continue infinitely. Well, until proven otherwise anyways. From this theorem, there's another case that we can investigate. The previous theorem says that a and b are algebraic. Then, a to a and b are algebraic, then a power b is transcendental. What if both a and b are transcendental? Are we going to get an algebraic as a result, or is it going to be a transcendental? Actually, there exists an equation that describes the relationship of such transcendental numbers. Euler's equation, where e to the power of pi I equals to -1. The I here is the imaginary number of complex numbers. It's amazing, right? How these two transcendental numbers and a complex number can form an algebraic number when they don't even associate themselves with algebra. Right from the beginning. These three are just the many transcendental numbers that exist, some of which can be much more complicated than our pi and e. At the last slide here, you can find a list of websites that I have found to be informative and useful references. Thank you for listening and have a nice day.